All right, we are going to do another RLC circuit example. This is going to be a little bit more complex than what you would probably see really in this class. But I wanted to show you an example that has a different alpha value and that has just a different characteristic of behavior overall. I feel like that's helpful to understand. So that's what we'll do. So we're going to start off with this circuit. You'll notice there's two resistors in this circuit. This is a voltage-driven DC circuit, and then you have a single inductor and a single capacitor here. I've written out the 7 steps for solving a first-order system. There is actually a different set of steps that's in the book for a second-order system. You really want to follow those, you can. And usually I actually teach a different set of steps for a second-order system. But this time around, I wanted to just show you that this process, it is the exact same. Solving a differential equation for this kind does involve these steps. So we're going to go ahead and do that. All right, so this is step 1. The circuit's been drawn. I've got my nodes labeled. Here I don't have any values. I don't have any initial conditions. I guess I can put some initial conditions in here just to make things more interesting. Here I'm going to do my 2 initial conditions that I like. The voltage on the capacitor at 0 is going to be 0, and the current through the inductor at 0 is going to be 0. So what I'm going to do here is I'm going to solve for IL. We've solved for VC in the last example. Solving for VC versus solving for IL, usually you want to do one of those two. I'm just going to be doing it the other way this time, just to give you a different perspective. So first step is already done, drawn the circuit. Second step, we're going to go ahead and move on to deriving the system equation. And to do that, we're going to have our constitutive equations, which are our system equations, and then we're going to have our component equations. Okay, so for our constitutive equations, here we have KVL and we have KCL. I'm going to go ahead and write out all of the KVL equations. So here we have this loop, we have this loop, and then we also have that loop around the outside. It's not really necessary to write all of them, but you know what? For the sake of clarity, it's probably a good idea. Here we have VS is equal to VR1 plus VR2 plus VL. And then we have VR2 plus VL is equal to VC. And then we have VS plus equals VR1 plus VC. So a little bit of a change up there. As far as KCL goes, we have 4 nodes. We'll go ahead and write those out. We have IS is equal to IR1. It's at node 1. We have IR1 is equal to IR2 plus IC. We have IR2 is equal to IL. And then we have IL plus IC is equal to IS. All right, so those are our KCL equations, and then we have component equations. And for our component equations, here we have 1, 2, 3, 4 components. So we'll go ahead and write out VR1 is equal to IR1 times R1. VR2 is equal to IR2, R2. We have C, I'm just gonna write the letter C. IC is equal to C, dVC dt, and VL is equal to L dIL dt. Okay, so these are all of our equations that we have for the system. All of these are enough equations in order to solve this system. So we're going to move forward now in trying to derive the overall system equation that we're going to be using for this problem to do all of our math. So here what we want is we want a forcing function on one side, and we want a function of our function on the other side, if that makes any sense. So here we'll have ILs over here, and we'll have our forcing function over here. Now we do have a voltage source, so I would prefer to use VS. Here we have two VS equations. I like the VS equation that includes VL in it because that just seems better to me, but you can get the same exact equation by using the other one. It just takes an extra step or two. So here I'm going to start off the one that has the forcing function and has the variable that we want, which here is linked to VL. VR1 plus VR2 plus VL. Okay. So that's great. I'm going to go ahead and do component equations immediately, really for all three of these. And what we'll end up with is, so this will be a component equation. What we'll end up is VS is equal to IR1 R1 plus IR2 R2 plus L DIL dt. Okay, so that works. Here now we can take some of our constitutive equations in here. This one in specific, it already breaks it out into IL, so we can just directly transfer this. This is currently in the form of IL. This one's going to take a little bit of work. So we're going to need another equation that has IR1 in it. We have this one, but we broke that one out in the component equation. If we just used it again, we would be jumping right back to where we just were. So that's not really all that helpful. The only other place we see an IR1 is right here. So we're going to go ahead and grab that one. So here, VS is equal to, and I will put in IR2 plus IC times R1 plus IL times R2 plus L DIL dt. Okay, now we know IR2 is equal to IL. That's a nice piece. So I should say this one is constitutive. That is an easy transition. This piece here that we don't have is IC. So here we've done component, constitutive. We'll switch back to a component equation just because any other place we're going to see IC over here on the constitutive side is just going to be rearranging what we just did. I'm kind of going back to the previous step. So I'm going to go ahead and take this and use a component equation. So here we have VS is equal to IR2 plus, here IC is equal to C dVC dt R1 plus IL R2 plus L DIL dt. And here that was a component equation. Okay, now we have VC. Now that we have VC, we go up and look over here and we say, okay, well, here is one function that has VC in it. That one's not really going to help us that much. The one that is going to help us is actually the one in the middle. We can, if you plug this one back in, it brings VR1 in here, and VR1 is what we're trying to get rid of. So that's why I don't want to go back to this equation. I will want to go into this one because it doesn't have VR1. We were able to get VR2 in terms of IL very easily, but VR1 is the one that's kind of a challenge here. If we didn't have VR1, the circuit would be a little bit simpler. So, okay, we're going to take VR1 out, and we're going to use this equation that doesn't have VR1 or VS. It could have VS in it, that we would just end up bringing over VS over to the forcing function side. That could happen, but here I just don't want to bring back in VR1. That's, really don't want that. Okay, so VS is equal to, and I can take IR2 and just go straight to IL. That's another constitutive equation. I'm going to go ahead and kind of factor this out, so it'll be R1 times IL, which you'll notice is, well, it is. That's what it is. It's that piece. Plus C, and then we'll take VC, so this will be C times the derivative of VR2 plus VL. And then I'm also going to plug in an R1 in here. C R1. Okay, just kind of factoring it inside. Plus R2IL plus L DIL dt. Okay, and here this was constitutive. Okay, now that we've done a constitutive equation, we do need to get rid of VR2 and we do need to get rid of VL now, because they're not in terms of currents. Here, this one is in terms of current, this one is in terms of current. I'm also going to take these two and combine them, because they both are an IL function, and quite frankly, that just pairs nicely. So we have Vs is equal to CR1 times the derivative, and here VR2, we go back to our component equations, and that is IR2 R2 VL, go back to our component equations, L DIL dt. Okay. Oh, trying to get on the ground here. Like I said, I was going to combine these two terms, so this will be R1 plus R2 times IL plus L DIL dt, and that was component equation. Okay. All right. Now here, the nice piece about this is this transitions nicely into IL, and then we have everything else as a function of IL. So I'm going to go ahead and do one more constitutive equation, and then we'll do a little bit of cleanup, and we'll have our overall system equation here. So Vs is equal to C times R1 times the derivative of IL R2 plus L DIL dt plus R1 plus R2 IL plus L DIL dt. And that was a constitutive equation. Okay, now we'll just do a little bit of cleanup. I'm going to break these two pieces out. You'll notice that we'll end up with a derivative right here. I'm going to combine the two derivatives just to clean this up, like what I did over here with the R1 and R2. Just trying to get into three distinct categories. You have your second derivative, your first derivative, and then your no derivative. But I'll do that. That'll be the last step. So, but first I got to do the derivatives and I got to separate these. So this is going to be C R1 R2 DIL dt. Okay, so that's this first term multiplied by the variables at the front, plus C R1 L d squared IL dt squared. Okay, so that's the second term there, plus R1 plus R2 times IL plus L DIL dt. Okay, so all I did there was factor. Now, what I'm going to do here is, we're done deriving this equation. I can go ahead and erase this top part. And then I'm just going to clean up this equation finally by taking all my like derivatives and putting them together. Okay, so here, I like derivatives. Here I have a DIL dt. There I have a DIL dt. This one is our second order, so we'll order this one first. This will be whoop, 1. This will be second. This will also be second, and this will be third. Okay, just to clean this up. So I'm going to move that now to the top of the board. So this will have C R1 L DIL dt. Oh, that's a d squared IL dt squared. Plus, then we have CR1 R2 plus L times DIL dt plus, and then we have our last term, which is R1 plus R2 IL. Okay, so kind of gross. It is what it is. And that is gross. This component here represents the impact of what the capacitor does. It's the energy storage actually in the capacitor. It's that component of this equation. This component here represents the energy storage that occurs inside of the inductor. That's why it's a single order derivative. And then here, this term represents the energy that is actually being released through the resistors. You'll notice they do all depend on each other. This one depends on L and C. This one also depends on L and C. So, kind of an interesting concept there. Now, I am going to do one more thing as far as deriving this equation, okay? I want to get rid of the term in front of this, and I want to put this in terms of 2 alpha and an omega naught. So in order to do that, I have to divide everything by CR1L. So Vs over CR1L is equal to d squared IL over dt squared plus CR1R2 plus L divided by CR1 times L times DIL dt plus R1 plus R2 over CR1L, and that's multiplied by IL, okay? Now, what we do, just like what we did in class, we want to set this in terms of some forcing function is equal to d squared IL dt squared plus 2 alpha DIL dt plus omega naught squared IL, okay? So that's kind of where we're working toward. I'm going to go ahead and just write that equation on the board there. And then we'll solve for our alpha value, our omega naught value, and then we have our forcing function. What you'll notice here is that your forcing function, which is CR1L, Vs over CR1L, is actually the, well, it's going to end up being the steady state value of how much current is passing through that inductor, but we'll get there. So we've got this. Now, here f of t is equal to Vs over CR1L. Alpha is equal to CR1R2 plus L over 2 CR1L. And then omega naught is equal to the square root of R1 plus R2 over CR1L. There we go. Okay, so that's fun. Now we got our zeta value, and that is equal to alpha over omega naught, which here the formula for that is super gross. So this is where it actually becomes easier to work in real numbers. So what we'll do is we'll say, okay, let's assign some real values here. I'm going to have R1 be equal to 10 ohms, R2 will be equal to 20 ohms, L will be equal to 10 henries, and C is going to be equal to 10 microfarads. Okay, nice, nice. So let's actually calculate out A then. Will give us a nice number to work with, alpha I should say. So here, alpha is equal to 10 times 10. So that's 0.0001 farad times R1 is 10 times 20 plus 10. So that ends up equaling 10.002 divided by 0.111 times 10 times 2 times 10. 0.002. So here our alpha value is equal to 0.002 divided by 0.002. This is equal to 5001. Okay, our omega naught value is equal to, so here we have omega naught is equal to square root 30 over, and here this is 0.0001 times 10 times 10. That's 0.001. So square root of 30, the answer is equal to 173.2. Okay, so we've just gone about this the exact same way as we would otherwise. No big shock here. But there is something that I'm going to do a slight tweak to. I'm going to go ahead and say, instead of microfarads, I'm going to go ahead and drop this down by a factor of 1. Okay. And I'm also going to drop this one down by a factor of 1. And what you'll notice here is things do start to change a little bit. Okay, so if we go back here, instead of being 1.002, this ends up being, well, 10.002. It ends up being 1.0002, and then that's divided by 0.00002. So what we end up with here is, this ends up being 50,000, and our omega naught value ends up being 30 divided by 17. Oh, dang, it didn't quite do what I wanted it to do. Drat. Sometimes I'm terrible at designing these circuits. That's a shame. Oh well. We'll go back to our original numbers. So this will be 10. This will be 10. But I'm also going to switch this one here into being 10,000. Because it is going to cause this problem to change. Alright, so doing the math again. I'm trying to create an underdamped system, in case you haven't noticed. Overdamped systems are just easy. Underdamped systems are a little bit more interesting. So here we have 0.00001 times 10 times 10,000 plus 10. This is equal to 11 divided by 2 times 0.0001 times 10 times 10 equal to 0.002. So our alpha is equal to 5,500. Okay, meanwhile our omega naught is equal to square root of, here we have R1, R2. So here we have 10,010 divided by 0.00001 times 10 times 10. So this is equal to the square root of 1,100,000. If I take the square root of that answer, it's still not an underdamped system. Let's flip. Switching this to 1, which changes this to 002, which makes this 550. And actually turns this into 2. So 2 divided by 0.0002, this becomes 10,000. And over here, that does not, yeah, it doesn't quite do the same thing. Well, bad. So actually, what I needed to do, if I want to make this an underdamped system, I have to make R1 fairly large. So I'll do that. Rewriting my numbers again. I'm going to make this underdamped. I will, and we'll solve that. So here we've got R1, we'll set this at 5,000 ohms. Okay, we'll set R2 at also at 5,000 ohms. L, once again, is just going to be 10 henries, and this will be 10 microfarads. Okay, so when I go over here to solve alpha, again, here, the top value is 10 plus 0.0001 times 5,000 squared. So this ends up being 260 divided by 2 times 0.0001 times 1,000 times 10, ends up being 1. So alpha value is equal to 260. Over here, we have this is 10,000 divided by 0.5. So square root of basically 20,000. It's 141. Dang it, I'm so close. Oh well. You know what? We'll just have this be an overdamped system. I guess I could just give you the alpha and omega naught values and just be like, here they are. That might be easier, but you know what? Doesn't matter. We've got this. Our zeta value here then is going to be 260 divided by 141.1. So here is equal to alpha over omega naught is equal to 1.843. All right. So there we go. We have our function, which is now this one. We have our alpha value, which we just have numbers for. We don't even need to use the expression anymore. I'm going to go ahead and move all of this to the top of the board so that we can work around it. Now you won't have values that change in the middle of the problem. I did that because I was just trying to get an underdamped system. I can't make it happen. So here we have f of t is equal to d squared il dt squared plus 2 alpha dil dt plus omega naught squared il. And then here f of t is equal to vs over cr1l. I guess we could write that out. Vs is equal to, I don't know, 20 volts. Then that means this is equal to 20 divided by 0.5, which is 40. Okay, and then we have alpha is equal to 260, and then we have omega naught is equal to 141.4, and then we have our zeta value is equal to 1.843. Okay, so that is the conclusion of the second step. I did take some extra steps in there because I changed the numbers and I put in numbers, but as I said, that is the conclusion of the second step. So now what we'll do is we'll go on to the third step. Because we've calculated omega naught and alpha, and because we know the value of zeta, we know that this is an overdamped system. Which means we're solving for IL. IL is equal to IL complementary plus IL particular. Because it's an overdamped system, we know that our complementary solution is going to take the form of A1 e to the S1t plus A2 e to the S2t. Okay, and we know our particular solution is going to take the form of A3. Why? Because this is a constant. Okay, and plus we know that at steady state, this is not unstable, so it should also be a constant value. Okay, that is done with step 3 then. And you'll notice this becomes really easy because as soon as we identify it's overdamped, then it's just solving for that. Step number 4 is solve for S. And you'll notice this also becomes easy because we have an equation for this in the book in terms of alpha and omega naught. Let me grab that equation real quick. The whole reason why we did all that work to establish alpha and omega naught is to make this piece a lot easier for us. It's nice because we already have the equations. Here, the S values are given by S1 is equal to negative alpha plus square root of alpha squared minus omega naught squared, and S2 is equal to negative alpha minus square root of alpha squared minus omega naught squared. Okay, so here we know all of our values for alpha and omega naught, so we can just directly solve for these by plugging in values that we have. We know derivations needed. Just plug it into a formula. And these, by the way, were the formulas 4.72 and 4.73 from the book. It does only apply to the overdamped and the critically damped case, I believe. You'll notice that there is no S value in the underdamped situation, but it gives you the formula for the natural frequency. Again, it's just using formulas from the book. And these formulas are derived such that once you find the value of alpha and omega naught, the solution process is identical. All right, so here we've got 260, gotta put a negative sign on that, negative 260 plus square root 260 squared minus 141.4 squared. And this first one is negative 41.812. And the second one, which is also a negative answer, the only thing it changes about it is that one of them becomes a negative sign, and this becomes negative 478.188. Okay, now these are actually fairly large S values. What this means is that this is going to reach equilibrium very quickly, comparatively. Now we could tweak this to reach a critically damped system, and then it would reach equilibrium even faster. But as it is, because these values are so large, it will reach equilibrium more than likely within a second. Okay, so that's step number 4. That was pretty easy. Not too terrible, definitely not as bad as deriving this. We'll go into step number 5. Now, as I've said, there's 2 approaches to step number 5. One of which is just looking at the system. One of which is doing mathematical derivations of the system using the given conditions, that being that at steady state, well, you don't have X behavior. You don't have a change in the current in the inductor. You don't have a change in the voltage on the capacitor. So here, we're just going to treat this as, we know this is going to be stable behavior. Just by looking at it, we'll treat this as an open circuit. We'll treat this as a short circuit. So really what we have is, if we redraw this, We have a system that looks like that. And our IL value is going to be the amount of current that goes through that resistor, which also happens to be the amount of current that goes through that resistor at steady state. So not too bad. What you have here is IL at steady state is going to be equal to Vs over R1 plus R2. Okay, I could derive that mathematically, but as I proved in class, as long as you know the system is stable, there's no need. You get the same equation, you just do it mathematically. So this is our particular solution, because this is what the steady state value of IL is going to be. So this is equal to ILP. Okay, and again, we're only looking at steady state configuration here for part 5. If I were to do this math, what I could do mathematically, the other side of it is, I take my original system equation, all of this, f of t is equal to d squared ILP over dt squared plus 2 alpha DIL over dt plus omega naught squared DIL comma p. I could add that comma p. And then what we do is we plug in the particular solution. Here we guess the particular solution is going to be a constant. And so as a result, this piece goes away, this piece goes away, and what you end up with is f of t is equal to omega naught squared times a3. If you divide this by omega naught squared, here omega naught squared is, I don't remember what the formula was for it, but if you divide 40 by this squared, you get a very small value for A3, and that very small value for A3, ooh, I did some math wrong somewhere. Oh, that's fun. What's my forcing function? It's 40. 40 divided by 141.4. No, that's actually right, because this ends up being Vs, and this is 10,000, so if 20 divided by 10,000, it ends up being like 0.0002, which would be what you get. So, no, I didn't do any math wrong. Hey, nice. We go ahead and solve this. This is 20 divided by 10,000, so the answer to that ends up being 0.002 amps, and that's a steady state current. And you'd find the same thing if you plug that in there. All right, so that's fun. Okay, so now we have our particular solution. I can go ahead and write that here, is equal to 0.002. We have our S values. S1 is equal to negative 41.812. S2 is equal to negative 478.188. This happened as a result of step 4. This happened as a result of step 5. Step 6 is to solve for the complementary solution. So I'm going to go ahead and erase the bottom part of the board here, keep the pieces that we need, and solve for the complementary solution. Now here we do need 2 pieces because we have both an A1 and an A2. We are going to need to use 2 initial conditions. So here are the 2 initial conditions that we have. We'll have to use both of them to solve this problem. Now the easy one is, here I'll write 6 up here because we're on step 6. But the easy one for us to take first is just to plug in this initial condition right here because it's already in terms of IL. So here we'll take our original equation. IL is equal to A1 e to the S1t plus A2 e to the S2t plus A3. We have all of those values aside from A1, A2. We plug this in at 0. So IL at 0 is equal to 0 is equal to A1 e to the S1t. That goes away because t at 0 just makes it go away. So this ends up being A1 plus A2 plus A3. So here A1 plus A2 is equal to negative A3 based on the initial condition that we have. Now that's one initial condition. We've done this one now. Ta-da! We do have to do this one. Now how do we solve for VC, well, now we have to solve for VC in terms of IL. Ugh. And some of this does go back to the original system equations that we already had. But VC, we know VC is equal to C, nope. My bad. We know that IC is equal to C dVC dt. Okay, so that's a fun piece of knowledge. And what can we do with IC? Well, not a whole lot. But what we could do also, a flip end of that is we could say, well, we know that VC is equal to VR2 plus VL. That actually is a much more solvable problem. Here this directly goes into VC. We know that VR2 is equal to IR2 times R2, and we know that this is equal to DIL dt, LDIL dt. We also know that IR2 is equal to IL, which means VC is equal to IL R2 plus LDIL dt. Okay, and now we have VC in terms of IL. So we will need to take the derivative of this equation, multiply it by L, and add it to this equation multiplied by R2 to get our VC value. So let's find out what DIL dt is. And we'll go back again. Here's what we have. I'm actually going to circle this because this is our first equation that we got from step 6. We're looking for a second equation. Second equation is going to be using this second initial condition, which is why we're trying to solve for VC in terms of IL. So, okay, we have, I'm going to go ahead and solve DIL dt is equal to A1 S1 e to the S1t plus A2 S2 e to the S2t, and then A3 goes away because it's a constant. So, if we take this and plug everything in, VC is equal to A1 S1 e to the S1t plus A2 S2 e to the S2t times R2 plus, no, that's times L. My bad, I'm writing this piece first. And then R2 times A1 e to the S1t plus A2 e to the S2t plus A3. So that is, this here is IL, this here is DIL dt. Okay, now we evaluate this at t equals 0. What we know is that VC at t equals 0 is 0 because that's the initial condition that we have. So this becomes 0 is equal to A1 S1 plus A2 S2 times L plus R2 A1 plus A2 plus A3. Okay, so this isn't nearly as pretty of a solution as the last one was, but that's because this system is slightly more complicated. All we've done is add a resistor, and we've already made the system way more complicated. So that's fun. This is why I said, you know, most of the time these types of circuits are going to be solved using nodal voltage analysis or mesh current analysis. It's because this stuff starts to get really gross really quickly. And if you can just plug a system of equations into a solver, it'll solve it for you and it'll find a numerical solution, and it's much, much cleaner than doing it this way. So, but I'm showing you how we do the calculations by hand and talking you through the solution steps. So this actually does kind of help you when you try to understand differential equations, and it is good to understand the concepts here. So the way that I would solve it is I would go into here, I would rewrite this equation as A1 is equal to negative A3 minus A2. And then anytime I see an A1, I would just replace that with 0 is equal to negative A3 S1 minus A2 S1 plus A2 S2 times L plus R2 negative A3 minus A2 plus A2 plus A3. Now, the nice thing is those two cancel each other out. But this is now solvable. We solve this for A2. We then plug in what we find for A2 back into this equation, solve for A1, and then we finish by writing the equation out. Okay, so that's how you would solve a problem like this. Again, this is more complex than anything I'm asking you to do in class, but I think it's good to understand. So I hope you have a good spring break. I'll see you all.